Welcome back. You are still with Mr. Mohapi. Now what we are moving on to are the activities based on the lesson we just had earlier. So we have there activity 1, whereby a learner investigates the photoelectric effect with the use of a photocell. The photocell is irradiated by light of different wavelengths as shown below. So looking at the first question there, we are asked to define in words the photoelectric effect. We explained or we defined photoelectric effect earlier, and we said that it is the process whereby electrons are ejected or released from the surface of the metal when light of a suitable frequency is shown onto the metal. And I said, in fact, I emphasized the word suitable frequency. That is a very, very important word in that definition, because it tells us that not every light will be able to eject or release electrons from the surface of the metal. So the light, or the only light that will be able to eject electrons from the surface of the metal, it is the light that will have a frequency that is greater than the threshold frequency, with the threshold frequency being the property of the metal. That is very, very important. Then moving to 10.2. 10.2, we are given a table there of the wavelengths. And then, as you can see, the full stop and commas should not be in the table. If present, there's no answer. Then we are going to ignore the commas and the full stops there. Then the question, the threshold frequency of the metal used in the photocell is 6,45 times 10 to the power 14. The average speed of the emitted photoelectrons are 2,78 times 10 to the power 5 meters per second. And then we are asked to identify the light that is used to irradiate the photocell. So we are given a table, meaning we will then calculate the wavelength of the light, and then check on the table where, to which light does that correspond to. To which light does the wavelength that we are going to calculate here correspond to, and then we'll then conclude at the end. So approach here will be, for 10.2, we write the data that is given to us. We are given the threshold frequency. We are given the threshold frequency, which is 6,45 meters times 10 to the power 14 hertz. We are also given the speed, the maximum speed of the photoelectrons, which is 2,78 multiplied by 10 to the power 5 meters per second. That is the information that we are given. Now let us look at the solution for this problem. What we need to calculate is the wavelength of the light. So with this information, we know we have what we have photoelectric effect formula, which is E is equals to the work function plus kinetic energy maximum. This is the photoelectric effect formula. But looking at the information that we are given, we are not given the work function. We are also not given the kinetic energy maximum. But we are given the threshold frequency. Then because we are given the threshold frequency, it means that we will express work function in terms of the threshold frequency. We are also given the what? We are also given the speed, not the kinetic energy. Then it implies that we will have to express the kinetic energy maximum in terms of what? In terms of the maximum speed. And we also want to calculate the wavelength. Then it means this energy of the photon at some point will then have to express it in what? With the wavelength. So let us get into it. So if we express, like I've shown you earlier, if we express energy in terms of the wavelength, then the formula will be hc over the wavelength. Why do we express it in terms of the wavelength? It is because we are looking, or we are calculating the wavelength. Then on the work function, Work function, we know it is related to the threshold frequency, so we are going to express this one in terms of the threshold frequency. We'll then move on to this. Kinetic energy, Leona, we are going to express it in terms of the maximum speed of the light. So it will be half mass of an electron and then V max squared. So the information, like I stated earlier, the information will direct you to what, how are you supposed to express the variables that are there in the photoelectric effect formula. So this is our unknown, and looking at this is the only unknown that we have here. We can then substitute everything and then calculate the wavelength and then check on the table to which light does that wavelength correspond to. So Planck's constant, as we know, is equal to 6,63 times 10 to the power minus 34, and the speed of light, like I said earlier, is 3,0 times 10 to the power 8, and then this is all over what? All over the wavelength, which then gives us the Planck's constant, which is 6,63. Maybe let me continue for space. Let me continue with this problem on the side. So I said we have E, which is equals to work function plus maximum kinetic energy. And then I said because of the information that we are given here, we are going to express work function in terms of the threshold frequency. Since we are given the threshold frequency, we are going to express the maximum kinetic energy in terms of the speed, because we are given the speed of the photoelectrons. And because we are looking for the wavelength of the light, then this energy will then be expressed in what? With wavelength. So it then moves to HC over what? Over wavelength, and then this becomes Planck's constant multiplied by the threshold frequency, plus here we want to express this thing in terms of the speed. We'll then have half mass of an electron and then V max squared. Now looking at this formula here, we can see that we have this is a constant, this is a constant, this is a constant, this is given to us, this is a constant, this is given to us. The only unknown that we have here, it is what? It is the wavelength. We can then substitute and calculate the wavelength. So here we'll then have 6,63 times 10 to the power minus 34 multiplied by 3 times 10 to the power 8 all over the wavelength. And then on this side, Planck's constant 6,63 times 10 to the power minus 34 multiplied by the threshold frequency that we are given is 6,45 times 10 to the power 14 plus half mass. Mass, it is the mass of an electron, which is equal to 9,11 times 10 to the power minus 31, sorry. And then the speed that we are given there, it is 2,78 times 10 to the power 5. So we have now substituted everything. We can then do our calculation and find our what? Find our wavelength. So the value of the wavelength, I'll just do a calculation here. So when we do our calculation, we can do it in this way. Maybe we can add the side on the right first. The side on the right, it is 6,63 exponent minus 34. And then this is multiplied by 6,45 exponent 14. And then plus, here we have 0,5 multiplied by 9.11 exponent minus 31. And then we multiply this by, don't forget the square on the speed there. We'll then have 2,78 exponent 5 squared, and then there is our answer. And then from there, we take this answer, which is the answer on this side. It is 4,286,283,7,862 times 10 to power minus 19. I do not round off at this stage because we are not yet at the final answer, so we need to be very, very careful. Then doing a calculation on the left hand side, it will be 6,63 exponent minus 34 multiplied by 3 exponent 8, then it gives us this is 1,989 times 10 to power minus 25. This is over what? Over the wavelength. So when you do your cross multiplication, on this side, we know this one is divided by 1 here. When we do our cross multiplication, then it will lead us to where we have this being divided by that answer on that other side. Yes, we are going to then divide this answer by 4,628,3,7,862, and then exponent minus 19. Then let us get our answer. We get our answer as 4. I'll move this thing just to express it in nano, because here it is minus 7, but we want to have minus 9 here. To have minus 9, it means this comma, I'll move it 2 decimals, and then we'll have 429 nanometers, or times 10 to power minus 9 meters, and then it is 429 nanometers. And then we go to our table and check to which light does that correspond to. As we can see, because of the rounding off there, we can then clearly see that the closest that is to that this wavelength is, it is of the what? Of the ultraviolet light. Therefore, light that is used here, it is light that has been used here, it is ultraviolet. Ultraviolet light. So that is how you identify the light. You check what is given in the table, and then you calculate for whatever unknown that you have. For instance, if we are given the wavelengths, it means you'll have to calculate the wavelength. If we were given the frequency, we'll then have to calculate the frequency to check to which light does the frequency that we will have calculated correspond to. That is our 10.2. And then moving on to 10.3. Very, very important question, this one. 10.3. They say the intensity of the incident light is now increased. They are increasing the intensity of the light. How will this influence the following? 10.3.1. We are asked, how will the increase in the intensity of light affect the ammeter reading? Ammeter reading, the ammeter reads the current. So if you increase the intensity, we have shown earlier that if the intensity is increased, then it means you'll have more photoelectrons at the end being released per second. And when we have more photoelectrons being released per second, then it means that the current will do what? Will increase. It means the current will increase because you are having more photoelectrons being released per second. And according to the formula, I is equals to change in Q over change in time. This is what I've shown earlier. If we increase the intensity, then it means we'll have more photoelectrons released per second. And when this increases, according to this formula, we then expect the current to also do what? To also increase. That is the influence of intensity on the current, or on the reading of the ammeter. And then moving on to 10.3.2, they say the influence of this on the kinetic energy of the photoelectrons. You'll remember I said that intensity of light only affects the number of photoelectrons that are released per second. It does not affect the kinetic energy. Intensity does not affect the speed of the photoelectrons. Then it means here the kinetic energy of the photoelectrons will remain the same, will stay the same as it has been asked there, stays the same. Reason being, intensity only affects the number of photoelectrons that are released per second. Intensity of light does not affect the kinetic energy of the photoelectrons, does not affect the speed of the photoelectrons. The speed and the kinetic energy of the photoelectrons will only be affected by the changes in frequency, and I said that to change the frequency of light, it means that you'll have to use a different light. If you want to increase the kinetic energy or the speed of the photoelectrons, you'll then have to use light of a higher frequency. So here, because the change was in intensity, then the kinetic energy of the photoelectrons will remain the same. Then 10.3.3, they say give an explanation to your answer. Like I said then, kinetic energy is only influenced. Kinetic energy is only influenced by changes in the frequency. And intensity does not affect kinetic energy of the photoelectrons. So kinetic energy is influenced yes, it is influenced by changes in the frequency of light, in the frequency of light, or someone might say intensity only affects the number of photoelectrons released or ejected per unit time. That is what the intensity will change. But then when it comes to kinetic energy and the speed of light, intensity does not have an effect on those, but it has an effect on the number of photoelectrons that are released per second. You can say per second here. Okay. Then moving on to the next question, or we are done with this one. So we need to know the influence of intensity and influence of the frequency on the what? On the ammeter reading. But what I said earlier is that whenever you increase the frequency or you increase the intensity of light, but this light that you increase the intensity of must be the light that is able to release electrons from the surface of the matter. I need to emphasize this point because even if you increase the intensity of the light, if that light is unable to release electrons or it has a frequency that is less than the threshold frequency, then there won't be any change on the number of photoelectrons that are released. The change will only come if the light that you increase the intensity of is a light that has the frequency that is greater than the threshold frequency. Please note that thing because it is very, very important, and many people, there are many learners make a mistake when it comes to that thing. Then moving on to activity number 2. It has now become a norm that this question is asked in a form of a what? In a form of a graph. If you are given a graph like it is the case now, it is important, especially when you have a straight line graph like this, it is important that you express the photoelectric effect formula in a form of a straight line graph. Let us show that. So we'll then have photoelectric effect formula. It is E being equals to work function plus kinetic energy max. Then let us check the variables that have been used here. So we have kinetic energy being our y, being on the y, and then we have what? We have also a frequency, but we do not have frequency here. So we'll then need to change this in to be in the form of a frequency, as you see it on the x-axis there. So we'll then have HF, which is equals to work function plus kinetic energy max. We are expressing this thing in terms of the frequency because on the graph we are given the frequency. Then we'll rearrange this formula. We'll then rearrange this formula to be in the form of a straight line equation, which is y is equals to mx plus c. So we know this is our y, and then this is our y input, this is our x input, and then this is the y. This is where the graph will cut the y-axis at. So when we express this thing, we want to make kinetic energy, since it is our y-intercept. Then kinetic energy must be made a subject of the formula, so that it takes this this format of y is equals to mx plus what? Plus c. So when we do that, we'll then have kinetic energy max being equal to HF minus, because we have transposed this one, we have taken this one from this side to that other side, minus the what? The work function. So once you have your formula being expressed or being rearranged to be in this format of the straight line graph, which is y is equals to mx plus c, you can then see that this one will represent the y input, and then x will then be represented by what? By frequency, and then this will be our y-intercept. This will be our y-intercept here. So here, if this is the case, we know m represents what? Represent the gradient of the graph. Because m represents the gradient of the graph, so it then implies that if you have a straight line graph of kinetic energy versus the frequency, then Planck's constant will be our what? Our gradient. If you have a graph of kinetic energy versus what? Versus the frequency of the light, you need to express this thing. If it is a straight line, you express it to be in the format of a straight line graph, and then check the variables. Your y will be the maximum kinetic energy, and then the Planck's constant h will be your gradient according to that graph, and then frequency will be your x coordinates, and then this one will be where our graph will cut the what? The y-axis at. So we can look at our graph here. We are having 6.8 there, and then if that graph is extended to cut the y-axis, it means that it will cut the y-axis at what? At the work function. Where it will cut the y-axis, that will be our work function. This is very, very important. So whenever you are given a graph, a straight line graph, and then maybe you are asked to determine the gradient of that graph, the first thing that you need to do is to express the photoelectric effect formula to be in the form of a straight line graph, which is y is equals to mx plus c, and then check what will represent the gradient, and then what will represent the kinetic energy, the y, and what will represent the x, and what will represent our c, which is our y-intercept there. Fine. I needed to explain this thing. Even if you can be given a graph maybe of the wavelength, let's say now you are having the graph of wavelength versus kinetic energy. Let's say you are having wavelength versus kinetic energy. If that is the case, we'll then have, if our now graph is Kmax versus our wavelength. So when we do this thing, we'll start first with what? With our photoelectric effect formula, which is E, which is equal to work function plus kinetic energy max. So it is a straight line graph that we will get here. E, because this thing, it is maximum kinetic energy against the wavelength, will then have to express this one in terms of the what? In terms of the wavelength. When we do that, we'll then have hc over wavelength. And then here we still have the work function plus kinetic energy max. So expressing this to be in the form of y is equals to mx plus c, then it means this kinetic energy maximum must be our subject of the formula. And then when we do that, we'll have Kmax on the side being equals to hc over what? Over the wavelength. Okay, this maybe it is 1 over here. That, and then plus what? Plus c. Okay, the kinetic energy versus 1 over wavelength. This should be kinetic energy versus 1 over wavelength. Sorry for that. And then once we have this, we can see that the kinetic energy maximum is our y. And then this can also be written as hc multiplied by 1 over wavelength plus c. And then this is kinetic energy maximum. So in this case, we can see that the graph is a graph between kinetic energy maximum and 1 over what? Over wavelength. So if you have your graph like this, then it means, not see, this is work function, sorry. This is our work function. And then because we have transposed it, it should be minus here. And then here it is also our minus. So now that we have expressed this thing in terms of 1 over wavelength, then you can see here in this case, hc, Planck's constant multiplied by the speed of light, that will be our what? That will be our gradient. So to find the gradient of the graph, you just have to express this thing to be in the format of y is equals to mx plus what? Plus c. Then from there you rearrange your formula, you'll end up, or you'll be able to identify your gradient, you'll be able to identify your y-intercept, and then your y-input and the x-input will also be identified. So whatever graph that you are given, as long as it's a straight line graph, try to put it, or try to make it to be in the form of y is equals to mx plus what? Plus c. Okay, now let us go back to the question. The first question, the threshold frequency of the metal is 6.8 times 10 to the power 14. And then 10.1, we are asked to define the threshold frequency. We defined what threshold frequency is. We said threshold frequency is the minimum frequency needed to eject electrons from the surface of the metal. The minimum, the word minimum is very, very important. If you leave out the word minimum, you are not going to get it right, or you are going to get 0 for that question. So the minimum frequency needed to eject electrons from the surface of the metal. That is the definition of what? Of threshold frequency. In the experiment, we are told that the brightness of the light incident on the metal surface is increased. How will this, okay, we dealt with this earlier, state how this change will influence the speed of the photoelectrons. We said that the brightness or the intensity does not affect the speed and the kinetic energy of the photoelectrons. The only thing that the brightness or intensity affect, it is the number of photoelectrons that are ejected per unit time. So here still we'll then have it remains unchanged, as the question is put there. It remains unchanged. So please note that brightness, which is your intensity, affects only the number of the photoelectrons that are ejected per unit per second. And the only time your speed or your kinetic energy will change, it is when we increase the frequency by using the light of a higher frequency. That is the only time your frequency or your speed and the kinetic energy will change. Then moving on to 10.3. 10.3, we are asked to show by means of a calculation whether photoelectric effect will be observed or not if monochromatic light of a wavelength 6 times 10 to the power minus 7 is used in this experiment. So we know that for photoelectric effect to take place, it means that energy of the photon must be greater than the work function, or frequency of the photon must be greater than the threshold frequency. So we are given the threshold frequency here, and then we need to calculate the frequency and see if this frequency that we are going to calculate, see whether that will be greater than the threshold frequency or it will be less than the threshold frequency. If this frequency that we are going to calculate, we are calculating frequency because we want to compare it to threshold frequency. So if this frequency that we are going to calculate here is greater than the threshold frequency, then it means that photoelectric effect will take place. But if this frequency is less than the threshold frequency, then it means that photoelectric effect will not take place. So let us go back to the question. Show by means of a calculation whether the photoelectric effect will be observed or not observed if monochromatic light with a wavelength of 6 times 10 to the power minus 7 meters is used in this experiment. So what then do we do with this? We then calculate the frequency. Frequency can be calculated if you have the wavelength. You can calculate the frequency being C is equals to F multiplied by lambda. And we know our C is 3 times 10 to the power 8, which is equal to frequency that we are looking for multiplied by the wavelength that we are given there. We are given 6 times 10 to the power minus 7. And then we calculate, we'll then have this divided by 6 times 10 to the power minus 7. And then we divide also on that other side 6 times 10 to the power minus 7. And then we then calculate our frequency. Our frequency will be this. This we will remove that. And then here we'll have 3 exponent 8 divided by 6 exponent minus 7. Then this gives us 5 times 10 to the power 14 hertz. So the answer that we get here is for frequency is what is 5 times 14 hertz. So we look at the question. On the question, the threshold frequency, where our graph cuts the frequency axis or the x-axis there, that is our threshold frequency. So the threshold frequency of this metal is 6,8 times 10 to the power 14. But the frequency of the light that we have calculated is 5. So because frequency of the light is less than, because we have just proved that with a calculation. Frequency of light is less than the threshold frequency. We can then conclude that we can then conclude that photoelectric effect will not be observed. So photoelectric effect not observed. Photoelectric effect, now it has not been, it will not be observed because the frequency that we have calculated is less than the threshold frequency. Okay, so we are using, like I said, we are using threshold frequency because that is what we are given. If we were given the work function, then it will mean that we will have to calculate the energy of the photon and then compare the energy of the photon to the work function. If the energy of the photon is greater than the work function, then it means a photoelectric effect will be observed. But if energy of the photon is less than the work function, then in that case the the photoelectric effect will not be observed. Okay, now we move forward to the next question. In the next question, that is 10.4, we are told that one of the radiations used in this experiment has a frequency of 7.8 times 10 to the power 14, and then we are asked to calculate the speed of an ejected photoelectron. Okay, then we start first by writing the photoelectric effect formula. You write the photoelectric effect formula, which is E is equals to work function plus half mass of kinetic energy max. And then we look at the information and the unknown that we are supposed to calculate. So according to the information that we are given for the light or radiation, we are given the frequency. Because we are given the frequency, it means energy of the photon will then have to express it in terms of the frequency. So we'll then have on this side HF, that is Planck's constant multiplied by what? Multiplied by frequency. We are expressing it in the frequency because we are given the frequency. If we were given the wavelength, then we'll express this energy of the photon in terms of the wavelength. Then the work function, we look at the graph there. We are given the what? The threshold frequency. We are not given the work function. So because we are given the threshold frequency, then it means work function will also be expressed in terms of the threshold frequency. That will be HF naught. Plus, we are not looking for kinetic energy, but we are looking for the speed of the photoelectrons, the maximum speed of the photoelectron ejected. Because we want the speed, then it means this kinetic energy maximum will then have to be expressed in terms of the what? In terms of the speed. So we'll have half mv max squared. This is very, very important to understand that if you are given the frequencies, then energy will be expressed in terms of the frequency, work function will be expressed in terms of the threshold frequency. But when you do the problem here, you start with this formula, the photoelectric effect formula first. So after this, we'll then substitute. We know Planck's constant is 6.63 times 10 to the power minus 34. And then this is multiplied by frequency that is given, that is 7.8 multiplied by 10 to the power 14. And then here we have 6.63 times 10 to the power minus 34. And then the threshold frequency. I said the threshold frequency, where you get it from the graph, where our graph cuts the frequency axis or the x-axis. That is your threshold frequency. So here we can see that the x-intercept there, it is what? It is 6.8 times 10 to the power 14. And then this is added to a half mass of an electron, 9.11 times 10 to the power minus 31. And then we have here Vmax squared. We have here Vmax squared. So that is how we will approach that problem. And then from here, we just do our calculation to calculate the speed or the maximum speed of the photoelectrons that are ejected. So we'll then have 6.63 exponent 34 multiplied by, okay, minus 34, and then this is multiplied by 7,8, which is the frequency of the light, exponent 14, and then this is equals to, so on the left hand side we have 5,1714 times 10 to the power minus 19, and then on this right hand side we have 6,63 exponent minus 34 multiplied by 6,8, which is our threshold frequency, exponent 14. It gives us, here we have 4,5084 times 10 to the power minus 19, and then we still have half into 9,11 times 10 to the power minus 31, and then Vmax squared. So that is what we are having here. And then we'll just transpose this one from this side to that side. We'll then have, when it gets to this side, we'll then subtract it from this. We'll have 5,1714 exponent minus 19 minus 4,5084 exponent minus 19. And then the answer that we get there is 6,63 and times 10 to the power minus 20 being equals to half into 9,11 times 10 to the power minus 31, and then this is Vmax squared. So this answer we then divide it by 0,5, that is half, which is multiplied by 9,11 exponent minus 31, and then it gives us, but remember we want the speed, not the square of the speed. We'll then put this inside the square root, and our answer there will be equals to 3,82, then it is 1, 2, 3, 4, 5 times 10 to the power 5 meters per second. So that is how we will do that problem. Okay, and then when we move back, we are done with this activity also. Then we'll look at the next activity. Okay, this one is the same as that other one. We'll do this last activity here. An experiment is conducted to investigate the relationship between frequency of the incident light on a metal and the maximum kinetic energy of the emitted electrons from the surface of the metal. This experiment is conducted for 3 different metals. Because they say they are using different metals, then it means the threshold frequency and the work function will be different. So there, as you can see, we have potassium, we have zinc, we have platinum. Each one of those, as you can see on the graph, it has its own work function, and it has its own it has its own threshold frequency. You can see that potassium cuts the frequency axis just before 0,5 times 10 to the power 15, and then zinc cuts the frequency axis just after 1 times 10 to the power 15 hertz, and then platinum cuts the frequency axis in between 1.5 and 2 times 10 to the power 15 hertz. That is what we expect. That is the expectation, that whenever you use different metals, then it means the work function and the frequency will be different for each metal. Then we are asked to answer the following questions, okay? Then 16.1 here, we are asked the name of the phenomenon on which this experiment is based. It is based on photoelectric effect. It is based on photoelectric effect. And then that is our 16.1 answer. That is photoelectric effect, because here we want we are using, or we rather are using light to eject electrons from the surface of the metal. So the principle or the phenomenon here, it is photoelectric effect. Then 16.2, we are asked to name the physical quantity represented by X on the graph. I showed you earlier, just before this activity, that the name of the quantity, that will be your y-intercept. I showed you that the y-intercept, if we express the photoelectric effect formula to be, or rearrange it to be in a form of the straight line equation, then your y-intercept will be your work function. So work function will represent X there. That is our work function, where our graph cuts the kinetic energy of the y-axis. Then 6.3, we are asked which one of the three metals needs incident light with the largest wavelength for the emission of the electrons. We are asked, we are asked to find, or rather identify, the metal from the three which needs, or with the largest wavelength to emit the electrons. We know that if you have a higher frequency, then it means your wavelength will be low. According to this formula here, C, which is constant, is given by F lambda. So if we can make frequency subject to the formula, we'll then have C over what? Over lambda. This then tells us that if the frequency is high, then wavelength is low. If the wavelength is high or is longer, then the frequency will be low. So that is the principle that we'll use to answer that question. We check the one that will have a higher, a lower frequency. The one with a lower frequency will then have higher what? Will then have higher wavelength or longer wavelength. So which one of the three metals need incident light with the largest wavelength? The largest wavelength. The largest wavelength, let us see. Then that will be what? That will be platinum. That will be platinum there. And then the reasoning will be on this thing that I've, not platinum, potassium, I mean, sorry. That will be potassium there. Okay. And then the reasoning, you then use this formula that relates the frequency and the what? And the wavelength, and answer it by saying the longer the wavelength, the smaller the frequency. The shorter the wavelength, the higher the frequency. Okay. And then number 16.4, we are asked to define the term work function. Work function is the minimum energy needed to eject electrons from the surface of the metal. Okay, we have done those definitions. I think we can now, in fact, I'm confident now that each and every learner knows his or her definitions by heart by now. Okay, now 16.5.1, we are asked to calculate the work function of platinum. Platinum, what do we have for platinum? For platinum, we have the threshold frequency. The threshold frequency of platinum will be between 1.5 and 1.7. That is where it, between 1.5 and 2. That will be what? That will be, our threshold frequency will be 1,75, but then we times this by 15, and then this gives us 1,75 times 10 to the power 15 what? 15 hertz. That is what we get there, because it is just in between what? It is just in between 2. It is just in between 2 and 1.5. So that is what we will then have. And then when you want the work function, we know work function is given by H multiplied by threshold frequency. that is 6,63 times 10 to the power minus 34. And then we multiplied by the threshold frequency 1,75 times 10 to the power 15 hertz. And our answer will be 6,63 exponent minus 34 multiplied by 1.75 exponent 14. Then this then gives us the work function, which is equal to 1,16 times 10 to the power minus 19, because this is energy and then joules. So that will be how we will solve this one, because they want the threshold, the work function. Work function is given by Planck's constant multiplied by threshold frequency. We have our threshold frequency, and then we have Planck's constant as a constant there. We then multiply the two, and then we get our answer as 1,16 times 10 to the power minus 19 joules. Okay, then moving on to the last question. Here the last question is, we are asked to calculate 16.5.2. We are asked to calculate the frequency of the incident light that will emit electrons from the surface of platinum with the maximum velocity of 5,60 times 10 to the power 5 meters per second. Here they want the frequency. So we start every time when you do this calculation, we start with the photoelectric effect formula. So starting with the photoelectric effect formula, and then we have here half m kinetic energy max. So we have E being equals to the work function plus the maximum kinetic energy. But looking at the information that we are given there, the work function of platinum we just calculated in 16.5.1, so we'll just substitute it. And then kinetic energy, we do not have kinetic energy, but we have the speed of the photoelectrons, meaning we'll then have to express this thing in terms of that speed, which is 5,60 times 10 to the power 5 meters per second. And then here on the energy, what we are looking for, it is the frequency. So it means this energy, we'll then have to express it in terms of frequency, and then that will be HF. Then this will be HF, which is equals to work function. We leave work function as is because we calculated it in 16.5.1, and then plus this one will express kinetic energy. We'll then express it in terms of the speed because we are given the speed. Then that will be half m e and then Vmax squared. So we have 6,63 times 10 to the power minus 34. And then the frequency is what we are looking for. Work function as calculated in the previous question, 1,16 times 10 to the power minus 19 plus half into 9,11 times 10 to the power minus 31. And then this is multiplied by 5,60 times 10 to the power 5 squared. Please do not forget the squared. And then we do our calculation to find the frequency of the light. So it will be 1,16. I'll do a calculation on the right hand side first. So 1,16 exponent minus 19 plus in bracket 0,5 multiplied by 9,11 exponent minus 31 multiplied by 5,60 exponent 5 squared, and then we close the bracket. We then have what? 2,588,448 times 10 to the power minus 19, and then here we still have 6,63 times 10 to the power minus 34. Then we divide on both sides by 6,63. 6,63 times 10 to the power minus 34. And then even on this side, we also divide by 6,63 times 10 to the power minus 34, and then our frequency then becomes what? This divided by 6,63 exponent minus 34. Then our frequency becomes 3,90 times 10 to power 14 hertz. That is the end of the activities that we have prepared today. I hope that this lesson will help you as you prepare for your final examination, and I wish you best of luck on your examination. Thank you very much. Until next time.